Alright, in this video, we'll cover the problem, number of provinces on LeetCode. So you'll see we're given n cities, and some of them are connected. If city A is connected with city B, then city B is connected with city A. Also, they're saying that if city A is connected with city B, and city B is connected with city C, then city A is considered indirectly connected with city C. So let's see if they have an example. No, okay, they don't have a useful example. But if we look at example 1, pretend that city 2 was connected to city 3. Then they're claiming that city 1 and city 3 are indirectly connected because you can go through city 2 to reach city 3 from city 1. And they're saying a province is kind of a group of directly or indirectly connected cities. So right now, in the actual example 1, exactly as they've drawn it here, we have this as one kind of province. But if city 2 and city 3 were connected, the entire thing is going to be one province, even though 1 and 3 are not directly connected. And so, we want to return the total number of provinces here. One note is the input is a little different from what we are typically used to. So you can see we're given an n by n matrix. Remember, n is the number of cities we have. It's called isConnected, and isConnected at I at j is 1 if the cities are connected, otherwise it's 0. So for example, isConnected at 1 at 2, like here, I'll write this explicitly here. Oops. We can say isConnected at 1 at 2 should be equal to 1, because there is a connection here. However, isConnected at 1 at 3 is equal to 0, because there is no connection between these two. There is one slight, weird aspect of this problem, which is that the examples here, they're numbering cities 1 through whatever. But in practice, I'm sure you know that array indices start at 0. So this is actually isConnected at 0 is this array. It actually doesn't matter what these cities are numbered. This could be 0, this could be 1, and this could be 2. So I'm actually just going to use that naming convention because it works a lot better with the array, the way that the array works. Okay, so unfortunately, these visuals kind of do the graph visualization for you. But even just on this description alone, you can recognize that there's an implicit graph here. We have a bunch of cities, so these are kind of our pieces of information. These are our nodes. They are connected in some ways by these connections here, and so that's how we're modeling edges between nodes. The format of our graph is different. It's not an adjacency list, but conceptually the idea is the same. This is just an adjacency matrix instead of an adjacency list. Okay, so now, if we kind of visualize this as we have this implicit graph with cities and connections between them, and we want to count the number of provinces, well, in our graph, a province is just a connected component, because it's a group of nodes that are connected either directly or kind of with indirect connections, where you can go through other nodes to reach some target node. Now, this question has basically become, given a graph as an adjacency matrix, return the number of connected components in our graph. We know how to do this. We know that we need an entry point into every single connected component, and there's no way for us to magically know which are the special entry points. So we're going to try every single node. From each node, we'll say if we've never visited this node before, that means we found a new connected component. So increment our count of connected components, and then mark that whole province, that whole connected component, as visited. So we can go ahead and jump into coding this. First thing I'll do is I will switch this to ES6 arrow function syntax. I'm also going to rename this to be city connections. Okay, so we need our number of cities, which they're defining to be n. That's just going to be city connections.length. Now, we're going to want a visited set here, and we will discuss a note about the visited set in a second. But we also need a num, num provinces equals 0, and we're going to return num provinces in the end. In between, we want to say, for each city, we'll start at 0, going up to cities number of cities, and just city++. Note that you could start at 1 and then do less than or equal to num cities, it actually doesn't matter. It's just that you're accessing values in the city connections array will be a little weird because you have to do a bunch of -1s, but it doesn't actually change anything. Now here we're going to say if we've already visited the current city, just continue, don't visit it. Otherwise, we say, hey, we found a new province. So we increment our counter, and then we need to mark the province as visited, which will be a separate helper function that we'll write in a moment. This will take in whatever city we're starting from. It needs the city connections adjacency matrix so that we have our graph representation, and then it'll take the visited set here. Now, the point I want to make about the visited set is that sometimes the visited set should be created inside of your traversal, your BFS traversal method or function. And the reason is because, once the BFS has concluded, you want to clear the visited set. You don't want to be reusing that visited set in future iterations so that the new BFS that you do in the future starts from scratch. But in this problem, if we start at the 1 node, then we explore its whole component, so we mark 1 and 2 as visited. Then we're done. We've finished our mark province as visited. We go to the next iteration of our loop, and now we're at the 2 city, the one with ID 2. At this time, we've already explored it when we explored the component or the province that city 1 is a part of. So we don't want to re-explore it, and we want to be able to know that we've already visited it. So that's why we're creating a global visited set here, instead of just creating one inside of our BFS traversal method. This is something that you should put some thought into when you're coding these questions up. All right, now we have our mark province as visited function. It takes in a start city, takes in our city connections, and it takes in our visited set. This is going to be our BFS here. So we're going to create a new queue, going to add our start city to the queue, and we're going to mark that start city as visited. So we'll say visited.add start city. Then we can do our standard BFS logic. So long as the queue size is greater than 0, we'll remove a node, we will process that node, and we will add neighbors. So removing a node is the same as always. We're just going to say node, or we can do city is queue.dq. We will process it, we'll come back to it, we'll come back to that step, and then we will iterate over the neighbor cities. So this is going to be a little bit different. When we have an adjacency matrix, let's actually draw one here. You know what, we'll use their example. So I'm going to draw a couple things out just so we can be very clear about how this adjacency matrix works. So we're going to rename their cities to be 0, 1, and 2 just so that the array indices actually work in a way that is useful for us. But the way this adjacency matrix works is, suppose we're at city 0 and we want to figure out if we have a connection to city 1. Then we can go to the row for city 0 and the column for city 1, and since this is a 1, right here they're telling us 1 means they are connected. So this means that city 0 and city 1 are connected with each other. You also could do the other direction, like go to row 1, column 0, but that's the same value. This matrix will always be symmetric about this diagonal right here. Anyway, so we can go to row 0, column 1 to get our answer. However, you'll notice that if we just take row 0 in our matrix, that gives us this entire array. And that is actually not all neighbors. Like this one right here is not a neighbor. City 2 is not a neighbor of city 0. So you might be tempted to name this like for each neighbor in that row or something. But that's not correct. These are just like potential neighbors. So I'm going to name this potential neighbor city. And obviously we're just going to go through every city. So we'll do 0. We'll start at 0. We'll do this so long as, and we can make some space here, so long as the potential neighbor city is less than num cities. We actually don't have the num cities here, so I'm going to create it. We'll come to the top. We'll just say num cities here is city connections dot length. Okay, now we come back to our loop. First, we need to figure out if we actually have a neighbor. And so is neighbor will be, we can do city connections. We'll do our current city. So that's like if we're at 0 and we're trying to figure out if we're connected to city 1. We take our matrix. First, we go to city 0. Then we do city 1 after that. So we'll do the potential neighbor city. And we want to know whether or not this is equal to a 1. we don't want to have a magic number because it's kind of arbitrary. Like, what does this 1 actually mean? So we'll declare a constant up here that will say connected, and we'll define that to be 1. So we're going to check whether when we go to city connections at city and then at potential neighbor city, whether or not we get connected, which is 1. So if we do get connected, then obviously this is a neighbor. Otherwise, it is not a neighbor. So we can say if not is neighbor, we can simply conclude. That's a simple check. Now, at this time, we know that we've iterated through every potential neighbor city. We have removed ones that are not neighbors. So anyone here must be a neighbor. So this is kind of where we do our normal logic in a loop that looks something like for const neighbor of neighbors. And what do we want to do? Well, we know we want to check if it's visited. So we'll say if visited.has potential neighbor city. Yeah, I mean, it's no longer a potential neighbor city. It is a neighbor city. So this is kind of up to you whether or not you want to do this. I would personally rename it like this so that we have neighbor city. So it's very clear now that we know it is a real neighbor. But if it's already visited, we can just continue. And the other note is we want to add it to our visited set immediately. And the reason is because there might be another node that is in the queue who has this neighbor city as one of its neighbors. And it would also add the neighbor city onto the queue because we actually don't know that the neighbor city has been visited if we did not include this line. If we wrote our visited.add line up here, then we could add the potential neighbor city or the neighbor city to our queue multiple times, and then it gets added to our visited set multiple times, and it's processed multiple times. Because when kind of future nodes are trying to add this neighbor city to the queue, they don't actually know that it has already been visited, since if we write our visited.add up here, we only mark a node as visited once we remove it from the queue, not once we add it to the queue. So we'll go ahead and do it like this, so that the second we add a neighbor city to the queue, we're telling everyone, hey, never add this city again. It is taken care of. And then the last step is we need to actually push our neighbor city onto the queue. Or sorry, not push. We're going to add the neighbor city to the queue, like so. Okay. Now we probably want to come back and fill in our process node step. And the process node is kind of like, what do we want to do for each node? Well, for each node, we just want to mark it as visited. And we're already doing that here. So the only node that would never kind of be as, come up as a part of this loop would be the very first node, which is why we're explicitly adding it to our visited set here. But in this case, we could just write, for this problem, no work needs to be done in the process node step. And the last thing we'd want to check is, do we want to do anything after we break out of our BFS loop? In this case, no, because the goal of this function is just to mark the whole province as visited. So if we break out, we've marked the whole province as visited. Okay, great. That should cover the core logic for this algorithm. As you can see, for the most part, it is a pretty standard number of connected components implementation. The main unique thing is that we are doing this loop here, where we have potential neighbor cities, because we have to deal with our adjacency matrix. So just a quick review of that. We're checking every city. We're checking every possible city that in existence. We're figuring out, is that a neighbor of our current city? By going to our current city and then that potential neighbor city in our adjacency matrix. And if that value is equal to connected, which means a 1, then we know that we have a neighbor. If we have something that's not a neighbor, we ignore it. Then once we have a neighbor city, then we can add it to our visited, then we make sure it's unvisited. And if it's unvisited, then we can separate like this. Then we add to our visited, and then we add to the queue. And that's kind of the piece that is unique compared to a typical BFS number of connected components implementation. So we can go ahead and see if this works. Okay, looks like it passes this case, and we can submit, see if it passes all of them. Okay, great, looks like it passes here. That's all for this video, and thank you for watching.